Okay, Year 12, and welcome to our second lesson for this topic, which is further differentiation. And in this lesson, we're going to look at the derivative of log functions. So last lesson, we learnt about the derivatives of trig functions. The derivative of sine x is cos x, derivative of cos x is negative sine x, and the derivative of tan x is sec squared x. Now, before we get on to our derivatives of log functions, we need to recall that the derivative of e to the x is e to the x. It's the only function that remains unchanged through the process of differentiation. Let's have a look at a couple of examples. Find the derivative of y equals e to the x plus x squared minus 5. And we want to go term by term. The derivative of e to the x is e to the x plus derivative of x squared is 2x. Take away derivative of 5 is 0. So our answer is y dashed is equal to e to the x plus 2x. Here we have a product rule. We have x squared multiplied by e to the x. So I'm going to let u equal x squared and v equal e to the x. Let's find the derivatives. U dashed is 2x, v dashed is e to the x. And we need to put it into the product rule. So remember that it is u times v dashed plus v times u dashed. Okay, there it is there. Let's just tidy that up a little bit. We can factorize it or leave it expanded. Either way is fine. Now recall the pattern of these derivatives. Now we did talk about this in Year 11. If we start with y equals x to the power of 4, the first derivative is 4x cubed, the second derivative is 12x squared, and then 24x, and then 24, and then a whole lot of zeros. But if we start at y is equal to x to the negative 1, the first derivative is negative x to the negative 2, second derivative 2x to the negative 3, third derivative negative 6x to the negative 4, and so on. So my question is, how did we jump from here to here? Or what did we differentiate to get x to the negative 1? What's the missing link? Well, the answer is log. Let's have a look at the proof. Consider the function y is equal to log base e of x. So there it is there. I'm going to take it out into index form. Do you remember how to do that? This means e to the power of y is equal to x. So I'm just going to turn that around. And now I'm going to differentiate this, but I'm going to do something a little bit strange. I'm going to differentiate x with respect to y. We normally do dy dx, not dx dy. But you learnt in Year 11 that it's fine for us to change the variables around. So we're just going to do dx dy. The derivative of e to the y with respect to y is e to the y. It's unchanged. Now I don't want dx dy, I want dy dx. So I'm going to flip both of these sides upside down like this. Now I've got dy dx. What's this? E to the y. Have a look back up here. It's x. And so the derivative of log base e of x is 1 over x, or x to the negative 1. It's our missing link. Let's have a look at an example. Differentiate log base e of x. Take away 5x squared plus sine x with respect to x. Term by term, that's 1 over x. Take away. 2 comes down, 10x to the power of 1 plus, what was the derivative of sine? Cos. There's our answer. 1 on x, take away 10x plus cos x. Example 2. Find the derivative of y is equal to ln, and then in brackets x squared take away 1. Now remember, this is just a short way of writing log base e. So it's the same thing. We have a chain rule here. The outside function is log base e. The inside function is x squared take away 1. Let's do the outside function first. When we differentiate log base e, we get 1 over x. So that's going to be 1 over x squared take away 1, because we don't change that inner function, multiplied by the derivative of the inner function, which is 2x. Pretty much there, I'm just going to put this 2x up on the numerator. So there's our answer, 2x divided by x squared take away 1. And example 3, find the derivative of y equals x squared divided by ln x. So we have a quotient rule. Let's let u equal x squared and v equal ln x. The derivatives are u dashed is 2x, v dashed is 1 on x. And here's the quotient rule. We want v multiplied by u dashed, take away u multiplied by v dashed, all over v squared. So substituting in, this is what we get. So this can be tidied up, 2x ln x, take away, one of those x's cancel, so we end up with x there, all over ln x all squared. Now let's just talk about this for a minute. We can't actually simplify that. If you think about it, ln x all squared is not the same thing as ln x squared. So ln x all squared, that means log x times log x, whereas this one means log of x squared. So we can't simplify it to that. We also can't write it like we write trig functions, like ln squared x. That doesn't even make any sense. So this one's out and this one's out. We have to leave it written like that. So our answer is 2x ln x take away x all over ln x all squared. Now we can differentiate other bases. We did learn this back in year 11 with exponential functions. So we know that the derivative of e to the x is e to the x, but if we've got the derivative of a to the x, all we need to do is multiply that by ln a, and this is on your formula sheet. Here's an example. The derivative of 3 to the x is just going to be ln 3 multiplied by 3 to the x. Similarly, we can differentiate logs with other bases. So remember, the derivative of log base e of x is 1 over x. If we have a different base, we're also going to have ln a on the denominator. Here's an example. The derivative of log base 10 of x is going to be 1 over x, and then I'm going to multiply by ln 10. We'll finish with one last example. Find the derivative of log base 2 of 2x cubed plus 5. So we have a chain rule. Our outside function is log base 2. Our inside function is a series of power rules. Okay, so the derivative is going to be, we're going to do 1 over 2x cubed plus 5, but we're also going to put ln 2 in there. And then we're going to multiply by the derivative of the inner function, which is 3 2s are 6, x squared plus 0. And then just bring this up on top, and there's our answer, 6x squared all over 2x cubed plus 5 in brackets multiplied by ln 2. Okay, that's it for this lesson. In our next lesson, we're going to look at combined and composite functions and also tangents and normals.